Hi, my name is Mike Cerrone, and today I'm going to get into explaining the standard library swap function and how users can write their own more efficient swap algorithms. And to be able to get into how that works, I first need to explain how class structures can work with pointers because those more efficient swap algorithms work off of classes that work off of pointers. Um, and along the way, I'm also going to get into explaining how to write exception safe code for some of the operations that are concerned with classes that have pointers. So it's three things, and let's get into it. Um, the first thing I will explain, I want to focus on looking at things from a simple point of view, because when we dive into the code and looking at the files and stuff, it can get even for me, pretty complicated and pretty crowded pretty quick. So yeah, to explain, one very common structure that uses pointers is a class that has a pointer to implementation. And the name of our class that has a pointer to implementation we'll call widget. And it'll have a pointer, which conventionally is called p-impl, pointer to implementation. And this will point to um, a widget impl class, a widget implementation class that's a lot bigger, is full of a lot more stuff. So um, there are a lot of benefits to using this structure. The main one, which I explained in another video called "Reducing Compilation Dependencies," is to do just that. If you One way to reduce compilation dependencies is to have classes use a pointer to implementation structure. Um, I can't explain it completely. It's just there's just a lot to it. I invite you to check out that video. Um, one thing, another thing that this structure is very helpful with is to do swap operations. So when we have a swap function, we are going to swap one object, which I'll call object 1, with another object, object 2. Um, the standard swap, which I'll indicate here, the standard swap is actually a pretty expensive operation. There are three copy operations that occur within it. And you know what? I won't actually show the code. I'll just kind of diagram what happens. So over here, so imagine a line here. On this left side is object 1 data. On this right side is object 2 data. So the first operation is to make a copy of object 1. The second operation is to then have object 1 be overwritten by the object 2 data. And then the last copy operation is to have that temporary that was a record of the object 1 data before it was overwritten by the object 2 data is then copied into object 2. At the end of the function, this data, which was just temporary, is destroyed. So in this operation, there are and not in the order that they happen, but there are 1, 2, and 3 copy operations. So if this is a very large object, you are going to be experiencing life in the slow lane, as Scott Myers likes to explain in his effective C++ text. Oh yeah, by the way, this, of course, is an item in effective C++. This swap stuff all goes back to item 25 for effective C++, which is consider using a exception safe swap. I'm pretty sure that's what it is. So what we can do to get rid of all these expensive operations is specialize how the swap function works, given classes that have pointer to implementation structures. And I think even if you don't know code at all, you kind of see where this is going. The general idea, the basic idea, is to specialize swap to in the case of pointer to implementation objects, to only do this whole swapping operation with the pointer to implementation object. And if we just have things happen as they normally would, given a pointer to implementation structure without a specialization of the swap functionality, we'd have the swapping and involved copying occurring both for the pointer implementation and the underlying widget impl object. Okay. Now that I've explained the general stuff, let me very quickly do some stuff here. So don't kind of look at all this just yet. What I'm going to type out here is that a representation of the standard namespaces swap function, just so we can kind of refer back to it when we're doing the rest of this stuff. So it's going to be, it is a template function, so we're going to templatize it. And we are going to be changing data for both these references that are passed into the swap function, so they won't be const. They won't be constant. They will be changed. So we're not going to type const before the parameters. So t reference to object 1, t reference to object 2, and then continuing to write our code here, we're going to make a generic type T temp object of object1, and then we're going to have object1 be equal to object2, and then we're going to have object2 be equal to temp. And that is it. Yes, that is it. So, as we'll see here, first copy operation here, second here, third here. That is it. And I will comment this out because I'm going to be compiling this file, and this could mess things up. So, as I was explaining, I need to explain how classes with pointers structuring works first. So I will do that now. Of course, as we all know, or if you're just learning this stuff, as you'll soon find out, anytime you're dealing with classes with pointers, you need to follow what's called the rule of three. And if another way to think of things is if you find yourself doing one of these three things, one of these three functions, you're going to have to do the other two. Now these three functions are copy construction, and then this one, which is copy assignment, and then this one, which is the destructor. So, why do we want to be concerned with having these functions be given specialized definitions? There already are default operations for all three of these special functions. In a normal class, what happens is when you do copy construction, which is initialize a class object to the values of another class object, normal copy construction is every member of the class being constructed is just copied over from the other one. Same thing goes for copy assignment, except you're not constructing, you are assigning. So you've already made the object, and now you're going to be assigning values to it. With destruction, you basically, a basic destructor is the data is removed from the stack, basically. I can see if you're just learning this stuff, you may be a little thrown off by that, but just keep going with it. Maybe put that in the back of your mind, and think about it later, and do a little Googling. So in the case of pointers with classes, there is some special stuff we got to do with copy construction, copy assignment, and destruction. And I'm going to make a blank canvas here. And so if we have our first object, there we go. Okay. we got our first object. We got our second object. They, they're both pointer to implementation structures. So they both are pointing to their data. Right? Okay. So in the case of copy assignment, if I say this object, is going to equal this object, then what it's going to do is take the address that the pointer has here. So it'll take the address and just give it to the first object. We don't want that to happen. That is a no-no. Big no-no, because then you have two objects. Both these guys are both pointing to the same data. This one goes away. That is very undesired, because client code is written and it's never expected that pointers to data is going to be the same, or you can't have it expect that. But for objects acting and behaving normally, we always make sure that they point to different underlying data. And in the case of, let's say, so one thing I think you're wondering right now is, okay, well, you're saying I can't just, get the value of the pointer from one object and assign it to the next for the copy assignment operation. So what do? And what we do is this stuff in my file. We'll go ahead and take a look at that now. So the stuff for copy assignment, what we were looking at on the whiteboard just now, is this function right here. And what we're going to do is say that the data that is pointed to by the pointer to implementation is equal to the data pointed to by the pointer to implementation of the right hand side widget, the RHS widget. So if we go back over to our whiteboard, and I'm going to go ahead and erase a bunch of stuff here. Make my eraser bigger. Whoop. Oh crap, I don't want to do that. Oh shucks. Wait, I gotta make a new layer. Okay, so we're gonna do the same stuff. So for copy assignment, we have our two p-impl structures. From what I explained in the code just a minute ago, we're going to have the underlying data pointed to by the p-impl be set to the underlying data of the right hand side. So this underlying data then has subsequent copy assignment operations happen for every subpart. So this is part 1, this is part 2, 3, 1, 2, 3, and the subpart of 1 is copied over to here. This second part's copied over here. This third part's copied over here. That's it when it comes down to how to do the three main operations. The other two. Well, I guess I'll explain it really quick. Um, yeah. Okay. All right. Sorry. I'm so used to looking at the code. I gotta kind of remind myself of looking at it and then um, being able to explain it visually here. So with copy construction, we don't. With copy construction, okay. With copy construction, um, with our Pimple structures, or this first one on the left side is a new object. So um, I'm pretty sure it doesn't have data yet, but let's just move on. So for copy construction, which is initializing this object, it's the first time it's ever mentioned in the code. What we're going to do is have a new copy and dynamic heap memory be constructed, copy constructed from the underlying object of the right hand side p impl object. So it's gonna be copied over here. Um, and then finally, just to follow up on the whole thing here with destruction, we want to make sure we have a destructor for a class that involves pointers, because very simply, if you don't properly release the underlying data, then you're going to have a memory leak. So when these structures go out of scope, out from the scope of functions, and they're no longer of use in the program, we want to make sure to release the underlying heap data. So we're going to call delete on this pointer, which actually will de it will call the destructors for all subcomponents that are involved in this object, and then deallocate the memory block and releasing it back into the heap as unallocated space. Okay, so now that we've gotten through all that good stuff, let us look at how to make the code exception safe. So you guys may have been able to see ahead of me where I had this line here that said this is not exception safe. It isn't. Let me explain why. And the best way for me to explain it is to show it in action first. So here we are on the main function that's going to be executed when the program executes, and we are concerned with this section that I'm cursoring around, and we're going to make one widget that's constructed from it's constructed from data or memory on the heap, which is indicated by the usage of the new here. New returns a pointer, and that's what's used as a part of the p impl structuring. And we're going to have 321 be some of the ints And 1 and 5 here, some of the ints of these two widget objects that we're creating here. And we're going to have this special um, class called always throws become one of the members as well. And what always throws does is, here it is right here. Always throws will perform a throw, perform an exception anytime that a copy assignment operation occurs with it. Okay? So, going back down here. So let's go ahead and build the program and execute it. Okay, we saw what happened down here. We're in the part on exception safety. We're going to have another part in the console output later. Thus the parts. Always throw has thrown. And what's printed out here is 1 and 5. And as you can see here, the 1 and 5 is being printed here in the main code. And it's showing what the two int values are of widget 1. Now, if we look at our code up here, widget 1 originally had 3 and 21. So this assignment operation that started to occur, it happened somewhat. So there was a little bit of copying that happened, as we can clearly see. Some of the values from widget 2 were copied over. But since what is happening here, the copy assignment operation is happening here, right? Which, if we look at the definition for it, is defined here. The object pointed by the p-impl of this object is being assigned to the object pointed by the p-impl of the right-hand side widget. And what that does is the widget impl underline objects, which we can see here, the copy assignment operations for the subparts are performed. In the case of the built-in types such as int, they are copied over in a fashion that can't be overridden because they're built-in types, and they behave like we would expect them to behave. A simple copy is performed. For always throws, we are getting the call of its own copy assignment operation, and that is what leads to the exception. So, a lot of stuff going on, and some of it's not good, like I was saying. And that thing that is not good is we're getting a exception happening and leading to one of the objects within our code to be in what's called an invalid state. So halfway through the assignment operation, widget 1 is halfway changed, an exception occurs, and it can't become fully changed. And this is very undesired in code, and in the rest, or in one of the other items of effective C++, Scott Myers gets into writing exception-safe code, and there's 3 different guarantees. First one is called the basic guarantee, which is that when exceptions happen within a program, the program becomes some type of valid state. The other, that's the basic. The strong guarantee is before a function that's exception safe, it's in an original state, let's say. When the function occurs and fully executes, either, given exceptions or not, either it will be in the new state completely, or it'll be in that original state, no in between. And then the third guarantee is the no-throw guarantee, which is using operations within functions that don't throw, like manipulating pointers. Manipulation of pointers is guaranteed to not result in exceptions being thrown. So, what can we do to make this code exception safe? Give me one moment. I'm going to mute myself and drink water. Okay. What we're going to do is comment this guy out, and we're going to write some new code here. It will be widget, a pointer to widget impl, which we will call p_orig for original, is equal to this object's p_impl. Then we're going to have this object's p_impl be assigned to the value returned by this new object we're constructing, or by the address of this new object we're constructing on the heap, indicated by the new, and then it'll be a new widget impl, and it shall be a new widget impl that is copy constructed off of the underlying data of right hand side widgets p_impl widget impl pointer. And finally, we're going to do a delete operation upon the data pointed by p_orig. So one thing about code is, like, there's a lot of stuff done that has a lot of reasons behind it, and the code looks a certain way. I think it's good to not be too attached to how the code looks. It's really more important to really see what's going on, and basically study what's going on and see that happening while you're looking at it. So let me explain what's going on. This widget impl construction happening here, there's a so there's a copy construction happening here, and basically, if there is an exception that happens by the operation of this copy construction happening, we're only going to have p_impl either get the pointer to the new data and have that new data be completely made, or the exception will happen and the pointer to impl here will still point to the original data. So if you're paying attention before, you can get an idea of what's going on here, and that is that we are making this code be able to deliver on the strong exception safe guarantee, and that is that given a function that's this function that's exception safe, it will either completely change to what we want it to change to, or it'll be like it originally was. So yeah, I mean, that's it. I mean, that's kind of the beauty of it. We make a pointer, like a temporary pointer, um, and then we have this operation happen, which, if in the case that the construction of this new widget impl object that's a copy of what's being assigned from does throw an exception, you know, it's not going to change this data. And then to clean up, we make sure to call delete, which is a consequential calling of the destructors for the subparts of what is pointed to by PRIDGE and a deallocation of the memory. The really important thing that I wanted to do for this presentation was to show the exception safe strong guarantee work and be shown in action where the exception occurs and we see things happening the way we want to. And I did that by having a bad allocation exception occur. And that is what I will show now. I actually need to comment this part out because I don't want this to be the source of the exception. I'm going to save my code and build it. And now we will run it. And just like I wanted, a bad allocation happens. Let's examine why that's happening first. Widget impl is a giant object. Why? Because it has two int arrays, which are 1, 2, 3, 4, 5, 6, 7, 8, which are 100 million ints long each. So an int is 4 bytes, so each one of these guys is 400 million bytes. Since these widget impls down here are being allocated on the heap, we are having two instances of 400 million bytes each, and I just want to make sure my math explanation is correct here. 1, 2, 3, 4, 5, 6, 7, 8. So that's 100 million. And the int 400. So yeah, 800. Yeah. So 800 million bytes here, another 800 million bytes here on the heap. So 1.6 billion bytes, or 1.6 gigabytes of memory with these two guys. I was doing my research and I was looking at how much memory the Windows operating system gives for programs in their heaps, and I researched that one of them was saying it was like 2 gigs, and sure enough, that is the reason why we're seeing the bad allocation here. Because this operation is making a third widget impl object, which is right here. We're adding on another 800 million bytes and trying to allocate it on the heap, of which there's already 1.6 gigabytes taken. So we're trying to have 2.4 gigabytes of heap space to be used, and there's only 2 available. So that's why we're getting the bad allocation here. I did like doing this. Like it's good to know the boundaries of programs and stuff. I mean, if you stay in safe sandboxes for too long, you're not going to be able to I think grow your ability to do code. Hopefully I can run with that, and I think a lot of people would agree with that mentality. The important thing here is that we have the strong exception safe guarantee occurring, and that is that even when this operation doesn't successfully occur because of the exception that occurred, we still have widget 1 maintaining its original state, where its original ints were 321, which we see being printed out here. So that's it for now. I'm gonna be coming. I actually have to stop talking now. I'll be back and finishing this presentation in just a little bit. But for you guys, it'll just be a couple seconds. So bye for now.